Nice to be here. Thanks a lot. My name is Juan. I'm a senior consultant with the professional services team at Lightbend. I'll be talking today about building microservices with Akka typed. This is the agenda for today. So first, some introduction on being reactive, what reactive applications look like, why this type of technology is a very good fit for reactive applications. I will be doing a lot of, not coding, but I will be showing a lot of code, very simple code. So I'd like to know, since we're a small group, I'd like to know how many of you are using Scala daily or mostly daily, or familiar with Scala? How about someone that's hasn't seen Scala before? Okay, so we got a few people there. Okay. That's fine. Again, the code is simple. I will try to explain what's doing. It'll be obvious to most of you for the most part. How about Akka? How many people have used Akka before? Okay, a few hands. Anyone has used Akka typed already? One person? Okay. So that's great. Thanks a lot. Again, I'll be doing an introduction to Akka typed with some short snippets of code explaining what the new API is all about. I am going to concentrate the talk on stateful microservices. I think this is the sweet spot for what Akka can provide and offer to the microservices world. You can do microservices with any technology, right? You can, especially these days, people are deploying microservices to Kubernetes or Docker environments, and you can do that with many different technologies. What Akka brings to the table that's unique and fairly powerful, I would say, is the ability to create stateful microservices. So I'll be talking a bit about that. And the consequence of that power is the ability to actually be able to scale your microservices in a cluster and have your application work as a unique application in a cluster. And finally, I'll just make some comments about running in production, and we'll have some time for questions. So with that, sorry. Okay. So who's Lightbend? And in case you don't know, Lightbend is the company that has created the Scala language, Akka, Play, Lagom, all these frameworks around the Scala language. We also provide, this is something that people don't know that much. We also provide a product called Pipelines that is all about data streaming applications in real time. That's that big box there that includes things like Spark and Kafka and Flink and Akka Streams. I am not going to talk about that piece today. My talk is centered on the Akka part of the reactive microservices. And we provide, of course, training, support, and professional services around all these technologies. So what does being reactive mean when we talk about a modern application? How many people have seen or read the Reactive Manifesto before? Okay, a few people. This has been around for a few years. It basically boils down to 4 traits about your applications, your modern applications. They're represented on this slide. I'll go real quick about over this. We want our systems to be responsive. The system should be, should respond in a timely manner, if at all possible. If it's completely down, it's dead. But if it's not dead, completely dead, it should actually respond with, the data that we're looking for, or maybe it's an error or a failure or something, but it should be responsive. That's the main goal of a reactive application. In doing this, it should be resilient. This means that it should stay responsive in the face of failure. If a database is down, if there's a bug, if something blows up in my application, it should still respond to the user and let them know that there's something bad happening. It should be elastic. What this means is that it should stay responsive in the face of, under varying workloads. So scaling up and down. If I have a lot of users, the system should still be responsive. And this is all enabled by architecting this applications as systems with a pattern which is we pass messages around in an asynchronous, a very nice decoupling of our components in the application and in the system. It favors isolation and also something called location transparency, which means that these components can run anywhere in a cluster of machines. And that'll be very important, as we'll see later, in Akka cluster. So it turns out that the actor model, which is something that's actually really old, it's from the 70s, and it got popularized again by Akka about a decade ago. This fits really well with that reactive manifest. An actor is basically a software component that can do only 3 things. It's very simple. It can actually send messages to other actors. It can create new actors, and those will be children actors of itself. And that has some implications that I'll go into in a few minutes. And also, it can designate the behavior to be applied to the next message. So it basically mutates behavior based on the message that you receive. Actors actually are a great way to encapsulate state in distributed and concurrent applications. And we'll see that as well. It's important to know that no actor goes alone. Actors actually work together in a system, in an actor system. That's represented here. It's usually a hierarchy in a sort of like a tree of actors where you have the root guardian. That's an internal Akka actor that is actually supervising everything else. And then you have the internal actors, which are under system. Those application developers don't have to deal with. These are the internal workings of the Akka toolkit. And then everything under user is the actual code that you write. Here's where you will write your actors. And they will also follow this type of tree structure. So you'll assign different actors for different purposes. And they have hierarchical relationships. And this forms a supervision hierarchy, where this is represented here on the upper right hand. If a child blows up for whatever reason or fails, there are ways to inform the parent and let the parent make a decision of what to do. It could actually say, well, stop that actor. I don't care about the failure. It could pause it until a certain condition is met. It could resume it, restart it. There's different things that you can do with your supervision. What this means is that these systems can be failing all the time and still working, because we compartmentalize the failures to individual, very specific components of the application. So that thing could be failing and restarting all the time, but the rest of the application might be working. I'm not saying that's ideal. These applications follow a let it crash kind of model. And we don't worry too much about being super defensive in our coding when it comes to catching exceptions. And so let's make a quick introduction to Akka type. And in doing so, actually talk about Akka Classic. So Akka Classic is the Akka toolkit that everyone has used for a few years. It's well known, and there are hundreds, if not thousands, of systems deployed to production worldwide for many years. So this is what a Hello World actor looks like. It's pretty simple. We have to basically create an actor system. One thing to note is that an actor system is something that you create once because it's fairly expensive to create. That's what's going to hold all your application. And then we can create literally millions of actors in our applications. Actors by default occupy very, very little memory, and you can have millions per gigabyte of memory in RAM. So you can spread out the application this way within your JVM. So an actor that does a simple hello world looks something like this. It extends the actor class, and it has a receive method that does a pattern matching on the messages that you receive. This one is probably not a great example, but I wanted to keep it simple. It's receiving a message as a string, specifically the hello string. And if it receives that, it'll print that greeting that says hello world in this case. And also, it will send that back to whoever called this actor. It'll reply with that greeting. So that's how you access the actor ref. An actor ref is sort of like a pointer to your actor. Because again, this could be running locally, but they could also be running in a different machine. So those actor refs are sometimes remote. And you do this type of, that's called the bang operator. You basically tell the actor the message that you want to send it. So does anyone know what the problem with this is? What is the big problem with Akka Classic? It's untyped. What that means is that this actor actually receives any type of message, right? So I am specifically pattern matching on hello, but if in my application, for whatever reason, down the line when I have thousands and thousands of actors, if this actor receives a number or some sort of different payload, a case class, an object, whatever, this will actually get swallowed, and it won't do anything. You won't see it because we're not doing anything with that message. It goes to something called dead letters. And yeah, you just won't know that that thing got sent there, and that's a huge problem. I've had this problem in production. I've had that issue where you don't know what's going on, and it's because of this, right? It's because it can receive any type of message, and it's completely untyped. So Scala, of course, is a language that prides itself in being super typed. It has a strong type system, right, and a very powerful one. And here we have a toolkit that is untyped. And that's been a bit of a problem for some time. So the Akka team worked for a long time, actually, to provide a typed API, which was fairly challenging, but they've come up with a very, very good solution. It looks fairly different from the previous one, so you have to get used to it. And I have to say that there are two styles in the code that you can use. I chose to use the more functional style because it fits better with Scala, in my opinion. But if you go to the documentation, there's a different style to receive the messages. So you might see that in the documentation. So what does it look like? It's basically every actor is going to be just an object. And it's going to have a protocol that you define in the form of case classes. And that means those are the messages that this actor can receive. And it won't be able to receive anything else different than this. So in this case, that greet case class is the only thing that this actor will actually be able to process. If you send it something else, that causes basically a compilation error, which is where you want to catch things when you compile your software. So it doesn't even go into runtime space. And then you define a behavior. Behaviors are basically how you process these messages. So in this case, we can say there's different ways to process this, and we'll see a few others. But here we say behaviors receive, and there's a context, which is that underscore. I don't care about that one. And then there's a message. And again, if we send it something that's not a greet in our code elsewhere, it'll not compile. It'll just say that there's a compilation error. And same thing, we print. We're printing the greeting, and then we say behavior same. This means that the next message is going to be processed by this same behavior. So as you can see, you can define several different behaviors and pass processing of messages from one to the other based on different conditions. And then here is how we use it. We can create an actor system. Actor systems are typed as well in this case. And in this case, the actor ref is acting as the actor system. They're the same thing for this example. So I create an actor system with a hello world greeter, which is that behavior, and I just pass it the greet hello. So again, that system bang greet hello. If I send something different from that, it would not compile.
So you send to a system?
Yes.
So send to Akka ref.
Yeah, so this is a simple example. I'll show later how you can encapsulate an actor system and then actors within it. In this case, they're like a top-level actor ref. So I want to talk about a few of the interactions, interaction types and patterns that you can use with Akka type because they differ a little bit from Akka Classic. This is the typical one. It's the one that we just saw in the previous slides. It's called fire and forget, and this is basically when something in my system sends some data somewhere, and I don't care if it gets received or not, if there's no response, I just pass on some data, right? So again, maybe this is something that has that fits your problem or not, but it's one of the ways you can actually interact with actors. So, for instance, we have this printer with a print me message, and I process that message similarly to how we did it before. And I create the top level actor system. This was your question. The actor ref is equals that system in this case, in this specific example. And then I can just pass on the messages. Again, it's the same thing that we just saw in the hello world. Nothing different. We just tell the actor, process this message, do something with it. Now, in many cases, we want to have a conversation between actors. We want to have a request and a response. So an actor, will request something, and another actor will reply with something else. So we have a request actor. Its protocol, its kind of message protocol is a request. And it takes a query with a string, whatever that is. And what's interesting here is that it has a respond to, that's an actor ref of a response. The response also has to be typed. And whoever gets that response has to speak that protocol, right? So this is where it gets a little tricky. The response actor has a behavior of response. It's the only thing it can actually receive. So this is why we will send a response from the request to the response actor. The problem here is that I actually put the response outside of both actors, if you can see that. It's at the top. So we've kind of broken the encapsulation of the protocol. There's something outside of the actor protocols that's a response that is shared by both. That's okay with this example, but if you code larger systems, that's going to be a problem. So for that, there's another interaction pattern that's called the adaptive response. And this is a bit more complicated, but basically we have a requester. Its protocol is a request like the previous one. It also includes the response. So the response belongs to the requester, right? When it gets a request, it'll just go to the to whoever called it and reply back with that information, with that response. And then the receiver, instead of actually processing a response, we process something called a wrapped response. We basically wrap the response of the other actor. This separates the protocols of the two actors nicely, and they're encapsulated within the same snippet of code. And then we do a behavior setup that gives us a context. And there's this function that is a utility for adapting responses that come back from an actor that I don't understand and putting them into my wrapped response that I do understand, which is this message adapter response, put that response into the wrapped response. And again, if I try to send something that's not a requested response, that will not compile, because that's the only thing I can receive. So in that case, having a wrapped response, I understand what that is. I can process it and do something with it. Let's see. Another one that's used a lot is a request response with the ask pattern from outside of an actor. Sometimes, many times in our systems, we have to talk to actors from outside of an actor. It could be the HTTP layer. It could be an external system. You just have to send something to the actor and get back information. Usually, that's done by using the ask pattern, which instead of an exclamation point is a question mark. The ask pattern is that. And it returns a future, right? So this is how you do it. It's quite similar to how you did it with Akka Classic, but basically, you have the same requester. And then, instead of another actor, this is just an application, right? This is a I actually forgot to, this actually wouldn't run because I'm just looking at it. It says object main, it should say extends app. to be able to run what's in here. But imagine this is all inside of a main function. And you create an actor system with the request behavior, with a requester. Now, in order for me to process the ask pattern, I will need a scheduler. I will need a timeout, because features will, they can time out. So I need to know what my timeout is. And I also need an execution context. This is basically, to simplify, the thread pool where my features are going to be executing. So what I do is I will talk to this requester, right? And I would expect a feature of a response. So I do system question, and then you pass a reference, which is basically your reply to. That's the second argument of my protocol, right? Respond to actor ref of a response. That's my future. And I just pass in as the first argument of this function the request with its payload. And then that's a future of a response, and I can just process that future. I can map it, flat map it, whatever you want to do it. Or in this case, do an incomplete. And when it completes, I will either print the value if it's successful, or if there's a failure, I can do something with that. So that's another pattern that's very useful. Any questions up until now? This is kind of quick intro. You'll have to get the feel of how this is used. I will be showing some more complex code, more realistic code in a few minutes. But I wanted to talk about stateful microservices with Akka type. Up until now, we've seen just actors basically talking to each other, sending messages and all that. But a real application always has to kind of deal with state, right? Store information somewhere. This is done with an extension called Akka Persistence. This is just part of Akka. You add the jar into your project, the Akka Persistence type, and you can actually use it. What this provides is durable state. So I did say that actors encapsulate state, and that is true. You can actually mutate the state of an actor, but if you put it in memory, when that actor dies, that state goes away. And that's fine for many cases. Not everything has to be stored in a database or on disk, but many other things have to be persistent. And that's what we use this for. Akka persistence is a very specific, has a very specific persistence model. It will append, it's an append-only persistence model, so it will keep adding things in a journal as events. Only those events that are received will be persisted, not the actual state. I'll explain that in a second here. And those events will get replayed when the actor restarts from the durable event journal, and they will actually compose the state. This is a great fit for a architecture pattern called CQRS and event sourcing, which I will explain now. So we're taking a little bit of a tangent here. This is more generic, more architectural concepts, but they're a little bit necessary to understand what's going on. So super quick introduction. We could spend quite a bit of time talking about this, how you use it, trade-offs and whatnot. But basically, CQRS stands for Command Query Responsibility Separation. And what that means in a nutshell is to separate your writes from your reads. Most systems have different scaling characteristics and characteristics from writing data to reading data. I think for the most part, scaling reads is a solved problem. You just do a stateless microservice, put a bunch of instances of that in a cloud system, put some load balancer on front of those, and you can just go, right? And you can do auto-scaling and things like that. The database for that, which is a read-only database, is very different from a write database that has to perform a lot of transactions. And I don't know if you guys have worked with databases that had to scale both for writing and reading. That is hard to do. Coming up with a schema in a relationship that allows you to scale in both is really, really hard. So what if we separated the writes from the reads and created schemas that are appropriate for scaling the writes and scaling the reads and making them fast and making them efficient? That's what CQRS is all about. Now, of course, this adds complexity, and you have a problem now because how this works is that the client issues a command, system, do something. The system will process that command. It will validate it, perhaps, and maybe reject it if it's not a valid command. At some point, it will produce some events, something that has happened in my system. I validated your command to perform a credit card transaction, and that's valid. And I produce some events, and I store those events in my event store. The event store is the source of truth of the system. It's what contains everything that happened in the system. And then I can actually stream those events as they come in to different containers of data based on the purposes of my read-side models. I can go to a big data cluster if that's something that I'm doing. I can go to a cloud storage, something like Amazon S3 or something like that. I can go to an API database. Maybe I put a REST API on top of that, and that's my read-only model, right? So this event processing is basically a projection of my events so that I create the state in the read-only model. And using CQRS with this event processing is that combination of CQRS and event sourcing. How this works, or to better explain what event sourcing means, we're going to take a very simple example. Everyone has a bank account, and this is a very trivial example, but I think it's quite on point. So let's take your bank account. If you go and say, deposit $100, that's a command, right? Of course, that needs to go through some validations. Your account is open and certain things. When you do that and that action is processed, an event gets triggered in the system that says deposited with a value of 100. That's an event that we store in the system, in the event journal. You can do that several times. You keep depositing money, and that triggers events of deposited. At some point, you want to take out some money. You withdraw some money from your account, and that triggers a withdrawn event. That gets also stored in the system, and so on and so forth. This can go on forever, and this is basically how bank accounts keep track of your balance. So the balance of your account is actually the state of this actor, right? But I'm not storing the state. Imagine if every time you went to the bank, they just did the operation and they rewrote everything. They wouldn't be able to tell you the transactions that happened in the last three months or 6 months or a year, right? So what if we did that for every system? That has a lot of benefits. The first one is that it's append only, so it's super fast. I'm always creating data. I'm never deleting anything. And also, I keep a history or an audit log of everything that happened in my system. So it has really great properties. It also happens to fit very well with how you scale writes in a distributed system, right? So let's take a look at what a persistent actor looks like in the akka-typed API. The first thing I'm going to do here in this slide is just introduce kind of the structure of the persistent actor, because it has a few pieces to it that didn't fit in one slide. So we'll be going through all of these in sequence. The first one is going to be the protocol. That's basically the commands that I can that this actor understands, and that's not different from what we saw before in the previous slides. It's basically a behavior, and it's some case classes. Then we have the events that persistent actor is going to be able to process. Those are the ones that I'm going to be storing in the event journal. There's going to be some state. When I replay all my events, those get processed, and I arrive at a certain state for my actor. So I will model that as well. And I have a couple of helper functions that are needed, which are the command handler. Every time I receive a command, I need to do something. And the event handler. Same thing. When an event gets triggered, what do I do with it? Basically, what's going to happen is I'm going to update the internal state of the actor with that. Last but not least, I will have to define the how to start up the persistent behavior, which is slightly different from a regular actor. And something that's optional that we'll see in the end is the supervisor strategy, because it's a little different from Akka Classic as well. So let's get. This is the protocol. Again, if you see, we're following the commands, events, state. That's what we're going to talk about in this slide. This one's pretty simple. So one thing I will notice that most of the time, the recommendation is to actually model your protocol as a sealed trait, and then a final case class that extends that sealed trait. That will allow you to do a behavior of command, right? And it will actually be able to receive several types of case classes, but which are very specific. They're not just any case class. So that's how you define your protocol. In this case, we're going to add a person. We're going to get a person. That one is a read-only command. That's not going to trigger any side effects, right? Because it's just, hey, give me the data. And just for kicks, let's modify the last name of the person. And we just pass in the new last name that we want to modify to. Someone gets married or something. The events that get triggered for this persistent actor are, again, very simple. Person added. So when I process the add person command, okay, it gets added with that data. And for example, the last name modified event will include the previous last name and the new last name. Maybe I want to capture that. And both of those extend a sealed trait event. And then the state, this is where things get a little interesting. In this case, it's going to be a case class, and person is going to be an option of person, because initially, when you spin up the actor, there's nothing there, right? There's no data. The first time you call an actor to do something, if you haven't stored any information, we want to model that with a none in that case. And that's what the default does there when we create this person state case class. And then it has this update function that will take an event and produce a new state. So in the case of the person added, I will create a new state with a sum of that person. And in the case of the last modified, I will basically modify the internal person with the new last name. Anything else that I receive, I will return an empty state. Does it make sense for the most part? How you this is a very simple example. In real life, this gets a little longer, but and I actually do this in all my code. I always do commands, events, state. I put that in in the section so I understand what's going on.
So when you call person state update as an event, you return a new object.
Yes. Mm-hmm. Yes. This is basically so that we're not mutating any state, right? Following kind of good functional programming principles, we create a new instance. Yeah, that's a good point. It depending on how you want to structure this. A lot of people put this update into the event processing, the event handler. Matter of style, yeah. So let's talk about the command handler, because this is the one that does something, right? And it always follows the same structure. The command handler, forget about the parameters for now. It's going to be a command handler of three things. It's going to be a command handler of a command, an event, and a state. So if you follow the previous slide where you have already defined those, I can process a command. That's a sealed trait for my actor. I will trigger some events, right? And then I will update some person state in this case. And then it has this function where it will pattern match on the state and the command that's received. So the commands that we could do here were add person and modify last name. In the case of add person, about the behavior, which is the final piece, how you put all of this together. Forget about the second half of the slide for now. The persistent behavior is defining a function. It's very similar to the behaviors that we saw initially in the regular actors. It just has a little bit more stuff into it. So it's going to be a behavior of that command. That's the type of information that I can send to this actor. We're going to do a behavior setup to get the actor context. It's a type actor context in this case. And then instead of doing a regular behavior, there's this utility, this object in the ICAP persistence API that's called an event source behavior.
And again, same thing. It takes a command, an event, and a state, and it has a constructor. It's an applied method on this object that takes a persistence ID, the empty state, and the two functions that I need to process commands and process events. So the persistence ID is what identifies my entity. This person actor or person entity has to be uniquely identified. So that entity ID, which is something I'm passing in, will become very important in a real system. It has to be unique. And then the empty state is my initial state. In that case, that person state class that I showed earlier, which will have an option of person, in this case, equals to none. And the command handler and event handler are the functions that I talked about in the previous slides. So that's how that plus all the other slides that we saw before is what composes your persistent actor in a very simple example. Now, let's say you want to do you want to modify the supervision strategy. In Akka type, the supervision strategy by default has changed. And when it fails, it'll stop the actor. It'll just stop it. Normally, that's not what you want to do in a persistent actor. Because you could have, for example, some network issue momentarily where your persistent actor cannot connect to the database, and then that throws an exception. And the default behavior for that is going to be stop this actor. So one exception just kills your actor, and you'll have to restart it somehow or call it again. Probably not what you want to do. So in this case, I'm using a supervision strategy that's a restart with backup, which basically tries to restart it with a schedule, but instead of doing it every second or something like that, you could actually, if there's a problem with your database, let's say, if you try to restart actors every 500 milliseconds, that's probably going to make the problem worse, because it's like a DOS attack on your database in a way. Your system is trying to restart all the time, trying to connect, and that could be problematic. So what it does is it has this exponential schedule where it tries in a short amount of time. If it can't succeed in that case, it will try sometime later, but much later, and so on and so forth. So every retry, it's going to take longer, up to a certain timeout where it'll stop. Because maybe your database is dead or something. By that time, someone has gotten a page or something. And then this is how you call it. Instead of using the behavior in your actor, you call the supervised behavior. And you just say behavior supervise, and then you pass in the behavior of your actor. And you say what supervisor strategy you want to use when it fails. Okay, so that's a lot of stuff. That's just for the persistence. Now this is augmented and complemented really well with using Akka cluster sharding. So Akka cluster allows you to distribute actors in a cluster, and I'll show a demo of what it looks like in a second here. But that's very useful. But if you couple that with persistence, then we have the holy grail, because then you can distribute your actors, your entities across the cluster, and that's how you scale your writes. How this is done is that every entity is guaranteed to have a single instance across the cluster. But you can have thousands of entities spread out in many machines. So that's what gives you the horizontal scalability. The problem we're trying to solve is applications that need to scale or applications that need to be very tolerant to failures under heavy load. And also, perhaps applications that need to be always available. Always on, and this is basically every application these days. Right? Every system that's business critical will have one, two, or maybe all three of these requirements. And in our case, we want to do this for both the reads and the writes, following the architecture pattern that I talked about with CQRS and event source. So let me show you this. I hope it's working. This is a simulation of an Akka cluster. This is running in an OpenShift cluster, which is a flavor of Kubernetes. And let me walk you through what it represents. The big circles that are kind of yellow, orangey, brown, are Kubernetes pods. Those contain an instance of the Akka cluster application. So this is an Akka cluster application of 3 instances. And they happen to be deployed to 3 separate nodes in 3 pods. Well, that's actually up to Kubernetes. Kubernetes could decide to put it on 3 different machines, the same machine. That's another level of distribution. The cluster will decide what to do with that. I didn't do anything, and this thing is changing on me for some reason. Let me explain the green ones. Those are the actual shards. A shard is something that is a group of entities that are treated together. They go in a group. They will be managed together by the Akka cluster. So the thing that was drawn before, I don't know why. Let me try to refresh this. Oh no.
The green shards, are they represented by separate actor systems?
Not actor systems. This is all one actor system that's distributed. So every node, every instance of it will start an actor system, but it works together. It has to be configured to work together. The shard, the green circles here are basically the shard regions that define where your entities go. I don't know if you, let me go back to the slides because this thing is not working for some reason. So these shard regions define what group of entities are associated with that shard. And when you send a message to the system, you have maybe one API endpoint and you send a message. And Akka cluster knows how to route the message to the correct entity. So actually the API call could enter through this node down here, but maybe the entity that is responsible for giving you that data is over there, right?
So the shards are internal to actor systems.
Yes.
We don't know about the blue things. Just get the reference to it.
You have to define in configuration your number of shards. That's important to decide because it will give you the distribution. And I'm speaking from memory, I'm spacing out a little bit now, but there's a recommendation of number of shards per number of nodes or something like that. So that's in the documentation ballpark. But yeah, once you define the number of shards, Akka cluster will decide where to put them, and it will spread out the entities across the cluster. So that simulation, what it was doing is it was actually stopping some of these entities. The entities are the blue circles. So in our example previously, those would be the people, right? The person entities. Let's say we have a bunch of people that we want to store in our system. We could do it this way. We're talking about millions of people, right? Like millions of users, perhaps, in a system or something like that. This is a way to scale that out for writing. And then the nice thing about this, and it's unfortunate that page crashed, but in this demo, you can actually click on one of these big circles, and that kills one of the Kubernetes pods. And it shows you how things will get rebalanced. And you don't lose those entities. Those entities actually get reshuffled to another node. Kubernetes restarts the pod, and then when it comes back up, they get rebalanced again. So we have some time later, maybe I can restart Chrome and try to show you that example. But that's kind of the idea with Akka cluster. Akka cluster sharding in particular. So how do we shard a persistent actor? We did all this work earlier, commands, events, state, command handler, event handler, behavior, supervision. And all we need to do is add this for sharding, and we can actually use it as a cluster sharded actor. There's some configuration associated with this that you have to put in your application, but from a coding perspective, that's pretty simple. So we need a function that tells how to start a shard region. And that's one of those sections of that visualization that I showed earlier. You need a type key to uniquely identify your entity type. And this is how you create it. The difference is that the actor ref is going to be of type sharding envelope and then my command, as opposed to an actor ref of command. That's the only difference. But even though that's the case, you can access the entity directly through this code. So let's say this is basically how you start up the application. You create an actor system, you start up sharding with the Akka cluster sharding extension. So you say cluster sharding of system. Then you start the shard region so that Akka cluster sharding knows that there's a sharded actor in your cluster. And you call one instance of the actor this way. You say sharding entity ref4, and you pass in the type key that we defined there, and then the entity ID. That's the unique identifier for that actor. That will actually know which one of those blue circles in that visualization it needs to talk to. And even though the call might come in from a different node in the cluster, it will actually reroute things to the correct instance of your entity. Let's see. I wanted to show you guys a demo in more depth with code to see like more like a realistic application. But before I do that, because we're running a bit long, I wanted to basically talk about just a few considerations for running in production. Okay, because these applications they're complex. And running them in production is something that a lot of people get trip over with. So for production deployments, Akka Cluster and Lagom. Lagom is a framework for creating reactive microservices that we also support. It's an open source project. And it basically encapsulates all of these concepts. And it's a very opinionated framework, and it basically avoids some of the pitfalls that you can actually do with Akka if you're not careful. It kind of guides you a little bit. So it's a higher level framework, but it's kind of follows the same type of concepts. So Akka Cluster application and Lagom applications are really a great fit for Kubernetes environments. You can actually, there's two levels of clustering in that case. There's the Akka cluster, that's a logical cluster in your application. Your application works as a distributed entity. And then there's the Kubernetes cluster, which is more about the computing resources, right? Where it's a scheduler that allocates cluster resources for applications. So you can couple the two. The way we do this is with a module called, by utilizing a module called Akka Cluster Bootstrap. It provides auto discovery features. So one of the things with an Akka cluster is that you have to define a seed node. A seed node is basically the first member of the cluster. And in local development or in a static number of machines, you would probably define, okay, these two machines are going to be the seed nodes. And every other node in the cluster needs to connect to those to basically say, hey, I'm a new member of this cluster. What else do you got? And it'll have a gossip protocol where every machine sees each other's state at the same time and get updates frequently and so on and so forth. But in a distributed environment, dynamic environment like Kubernetes or cloud environments, we don't have that. Machines are virtual machines that come and go, they die, they probably should die every day or so. I mean, we have a bunch of computing resources that are dynamic, and we need to be able to form the cluster in those environments. So this uses the Kubernetes, in this case, the Kubernetes API to sort of detect each other as the cluster gets formed. And the first one will actually join itself and form a cluster of one and broadcast through an API. I'm here, there's an instance here. And as other nodes are joining, they will see that and start forming the cluster. So that's how this works in production. Something else this is actually really dangerous, and most people don't realize. It's not a question of if, but when you will get a split brain. A split brain in a distributed system happens when you have a cluster of machines, and then all of a sudden there's a network partition, and a part of your cluster doesn't see the other part. By default, or in many cases, Akka will actually stop sending messages to the nodes that it doesn't see, but you can end up with two clusters. Subcluster A and subcluster B, they don't see each other, and they think that they've lost a few members, but they operate as, this is not like a master setup where there's a single, arbiter for the cluster. It's a gossip protocol, so all of them have to see the same thing. But if 3 see one thing and 2 see another thing, they think they're the remaining surviving cluster. And then the danger is that in your system, you could actually end up sending messages to both. In a persistent situation, that's very, very dangerous because you can end up with data corruption. So this extension that Lightbend provides allows you to automatically remove unreachable nodes in the cluster. And it makes the correct decisions based on different strategies. There's like 6 strategies: static quorum, keep majority. So that one, for example, if there's 3 nodes in one side and 2 nodes in the other, it'll kill the side that has 2 nodes. There's different ways to resolve this issue with a partition. Some of those use the Kubernetes API to kind of defer to the surrounding infrastructure, the decision of what nodes to kill, basically, to remove from the cluster. And it's something that if you go to production and it's a mission critical system, you should certainly think about implementing. The other one that's really, really useful is another commercial extension that Lightbend provides, which is Lightbend Telemetry. And this is basically only configuration. You don't have to change your code. And you configure a bunch of metrics. Your application gets instrumented at runtime, and it provides, and we actually provide these dashboards in Grafana that tell you things like, number of messages received, how busy the mailbox is, requests per second, a bunch of stuff about the JVM as well, JVM metrics, and so on and so forth. So, if you're interested, take a look at that. And I wanted to go back to that code demo just for a couple of minutes. And for that, I think what I'm going to do is first, before showing the code, let me see. So I have, these are 3 terminals, and they have 3 instances of the application that I'm going to talk about starting already. So it's basically mimicking a cluster of 3 in a way, 3 instances, 3 nodes. There's a Postgres database and a Cassandra database starting in the background with Docker containers. The Cassandra database is for the write messages and events. It's going to persist those events. And the Postgres database is to actually project those events into a read model. So that application should be running, hopefully. And I'm going to show it. I'm going to show what it does. It's very simple. It's basically just an API. So I'm using Postman just to send some API calls, REST API calls to the system. So for example, let's say I want to get this image 1. By the way, I didn't say what the application does. It's basically, you could say it's a cloud-based image management type of system. So in this case, I am requesting that image. It doesn't exist. I return a 404, not found. That's because the application doesn't exist. Oh, sorry, the data doesn't exist. So I'm actually going to upload it. And for that, again, I'm going to use Postman to the images endpoint. And I'm going to, I haven't tried this. I love just taking risks. I took a picture from the window earlier of the street. It was like nice light and all that with my iPhone. And there's this picture here, the building that's kind of outside over there. And we're gonna create that one and send it. So I get a 201 created, right? That's a good sign. And I'm going to actually get that now. See, so I think I got to change this to building1.jpg instead of image1. Let's see if I can do this. Building1. And I get that image back. That's cool. So one thing that someone with sharp eyes might have noticed is that I am uploading through localhost 8080, but actually retrieving the data through 8081. And those are basically two of my instances of the application. One is running on port 8080, the other one is running on port 8081. So this thing that I talked about the API getting the request from the user through one node, but the actor actually running in a different node, that's basically happening here. But you don't notice that.
This is Postman.
Yes, this is Postman, yeah. And then you can delete as well. I mean, there's nothing really exciting about this, but actually this is one's gonna fail because I didn't change the name. It says bad request. So, oops, let's see, building one. So I can send that, I get a 204 from that request, and then if I try to get this, I should go back to not found, because I deleted it. But in my persistent event journal, all those events got persistent. So if I wanted to go back in time, I could see, oh, someone created this image at this time, and then it got deleted this other time. So I'm actually storing the history of everything that happened in my system. And finally, just to give you a sense of what that looks like real quick, it's very similar to what we saw earlier. This is my image entity persistent actor with my commands, my events, image added, image removed, my command handler, very similar. I pattern match on the commands, I persist, some side effects. The get image is a read-only command. I just return the image in this case. Same thing with the event handler, and same thing with the behavior. Supervised behavior and the start region. Same structure that I showed for the person entity. Now, this system has two actors actually. I've separated concerns. This one deals with the bytes of the image. I also implemented some utility functions that actually extract some metadata from that image, like the ISO, the focal length, some kind of photography-related metadata. And that's done in the metadata entity persistent actor. Same thing, commands, events, very simple, very similar. Now, what's interesting is that I only talk about the write side. But what about the read side, right? Because this, yeah, I can get that image back. But what if I wanted to get the metadata? Do I call that actor as well? Or what if I wanted to do a search by focal length of all my pictures? You can't do that with the right side, right? Because every entity only deals with the data of that individual entity. So what you have to do is, when you get all those events, you have to project that information into a container, a read-only model that serves those other queries that are like aggregations and filtering and things like that. So that's something that's done here with a resumable, I call it resumable projection. This uses akka persistence query API, which hasn't changed for akka type, it's the same thing. And it basically, just to keep things short, I need to save an offset. So when I read events, I need to know how many I've read already for a specific type of persistent actors. So when I save the metadata events, I tag all of those events as metadata, and then I can read all of those together in a stream of events, which is what I'm doing down here. Run query stream, and this is akka streams basically. So I'm reading the journal, and I'm doing events by tag. All my metadata events for all my pictures are going to be tagged by metadata. So every time the system throws one of those, I will actually project it through this stream of data. And what it does with this project event function is, it depends on your implementation. In my case, I'm inserting that into a PostgreSQL database. So, and this is the last thing I'll do, I promise. I'm going to take another image, different one. Image one, this is an image I took this summer in Lisbon, Portugal. So I created that. That should have created another entity with its corresponding events. And then if we go to Postgres, we should get some data here for the data that was created. And this is that projection where I'm streaming the events that have to do with metadata. And every time there's an event there, I will actually insert it to Postgres. Now, what happens if I send a delete command to the right side? There's another event that's image deleted and metadata deleted that will trigger a delete on this read-only database as well. So that way you keep both things in sync. It follows an eventual consistency model, so there's a lag, right? There's a little bit of a lag between your write model and your read model. And a lot of people struggle with that, but you would be surprised how many systems can actually accommodate this type of architecture. And you can scale write side and read side independently. They actually don't know about each other, so it's a nice decoupling of both sides. And with that, I am done with the presentation. Thank you very much for your attention. And if you have any questions, please fire away.
So how did you configure persistence? Like you were saying, you're using Cassandra for the write persistence. So where is that actually?
Yeah, let me show you real quick. Yeah, great question. This is a little weird for me here, but I'll find it. So it's on resources, application.conf, and there's a bunch of configuration here for Akka. Here's a persistence configuration. You have to say which journal plugin you want to use. So in this case, it's the Cassandra. I didn't talk about snapshots, but one thing that can happen is if you have thousands of events, every time an actor restarts, if it has to replay thousands of events to kind of rehydrate its state, that would be time consuming. So you can actually create snapshots of the state at intervals, so that when it restarts, it'll read from the last known snapshot and only replay the events that have happened after that. So you do actually store the state at intervals in this case. And that's done with the snapshot store. You can do that in the same database, in this case, Cassandra. There's some application configuration, HTTP stuff, and then the Cassandra journal and the Cassandra snapshot are configured here. So the contact points, in this case, this is actually the default configuration, localhost, but I also have an environment variable where I can pass the Cassandra cluster hosts. So those three terminals had that configured for my Docker environment. It's an IP in my VM. And there's some other stuff. You can do authentication, things like that. Same thing for Postgres. I think I have it here. Yeah. So you have a database configuration, and you can define your host, port, user password, your type of connection. This is useful because then, for example, if I want to do testing, I can put a different DB config here. I think it's here. And I'm using an H2, which is an in-memory database. So I can run my test locally with an in-memory database as opposed to like having to stand up a Postgres database. Same thing with the right side. There's an in-memory Akka persistence plugin that I can use for that. I think, yeah, it's here. So for testing, I'm not spinning up Cassandra, I'm spinning up Postgres. Yeah, so this is an example. It's not an official Lightbend example. I just want to make that clear. But I can do this. Let's see, github.com. Sorry, it's a little hard to type from this angle. It's got a couple of bugs. I will probably put a couple of tickets for that just so so people understand that, there's a couple of issues. There's not a lot in terms of instructions or README. It's a private repo, so something I've always wanted to do this, like live. Let's make it public. All the cool kids do this, so yeah. What is that? Come on, look at that. Pixels. Yeah, so I mean, it's out there. Again, it's something I've been playing with, in part because I like photography a lot, and I wanted to kind of mess around with images and whatnot. Something I haven't shown is, I know we're running out of time, but just for kicks. So I can, let's see, that one is not there because I deleted it. So let's add it again. Real quick, okay. I can get the image and I can say, hopefully this works. Mono, Chrome equals true. And I get a sort of a black and white picture. Sort of. Yeah, this works better with like real pictures, not iPhone pictures, but my code for this is like a super simple Java 2D stuff that's not robust. So,
How would you go about when the number of entities in your system becomes so large that there's the memory, it would just scale indefinitely?
Yeah, it's a great question. So thanks for that question. I should have talked about this. There's something, and I didn't implement this in this example, but I probably will at some point. And it's in the documentation as well. It's called passivation. So an entity can get passivated after a certain amount of time. What that means is that if it hasn't received a command in 2 minutes, let's say, it will actually passivate. It will stop. It'll be, out of memory. In that case, the state gets removed from memory. It can get garbage collected, basically. Mm-hmm. And that way, you can keep the number of actors down, of entities.
And the next time it's accessed, it will reload.
It will reload. It will rehydrate the same entity, a new instance, but like the same data. Oh, look at that! This one's back to life, maybe. Yeah. See what's that? Those are dying. Like there's some that disappear, and then they'll come back. That's the passivation. In this case, it's accelerated just for demo purposes, but that's how it happens. They're the original ones. There's a finite number of entities here. I'm not sure how many, but yeah.
Why do they come back on a different chart?
Sorry?
Why do they
I think that's an issue with the ID that's displayed in the front end. Yeah, it's not. There's some crazy D3 code here.
Okay. So it's coming back to its original place, which is not.
It could actually come back in a different place. Let me try this actually. Let's try to kill one of these guys. So yeah, I just killed one node, right? And what happens is that the entities got reshuffled. See how they show up? I mean, they take a little bit of time. In the meantime, if those entities are receiving messages, they get buffered up to a certain point, and then as soon as they come up, they will receive that information. And now the Kubernetes has restarted that pod, and Akka node, it joins the cluster, right? It joins the Akka cluster. And then the entities get reshuffled so it's properly balanced. And this happens without you knowing about it, pretty much. I mean, you can know about it, but you'll have to.
So if you're running Kubernetes and using like Cassandra's running in a different pod than.
Yes. Actually, I wouldn't run Cassandra in Kubernetes in production. Most people actually don't do that. But Just because it's hard to run stateful services in Kubernetes, for the most part, we actually, as part of the pipelines product, we offer an operator for Kubernetes that allows you to run Kafka inside of Kubernetes, and people do that in production very effectively. Cassandra, since it's the event journal and it's very critical, that's your source of truth, I don't think it's there yet. So most people actually run it outside of the Kubernetes cluster. But it's in your network, right? So you have access to it somehow. Yeah.
Is there support for distributed tracing in the after system?
Yes, great question. I'm not going to pull up I'm not going to look for it, but the Lightman telemetry actually supports that. It gives you support for distributed tracing within your system. That includes Akka streams, Akka HTTP, Akka actors, Akka type actors, and it has support for 2 backends that I know of, Jaeger and Zipkin. Yeah. So you can visualize what happened with your request across your microservices. That's actually fairly critical, if you ask me, when you build something of a certain size. Yeah. Any other questions? Cool. Well, thanks again for coming.